Now let's prove the second of these basic properties of limits about the product, the limit of the product of two sequences. So now what we need to do is let's do the rough work first and see what happens. So what we need to do is we need to take a and bn and look at how far it is from ab. So what I'll do is I'll look at a and bn minus ab in absolute value. Now we need to make sure that this difference is not too big. One trick that one uses is to break this difference up into two parts and try to control each part separately. So this is a common strategy of divide and rule. So a and bn, and this should be close to, I guess, a and b if n is large, right, because then bn would be close to b. Okay, so I have subtracted a and b, let me add it back, and so I have not really done anything, and then let us subtract ab. So now you see what has happened is I have written this in two parts, as a and bn minus a and b plus a and b minus ab. So using the triangle inequality, I can write this as a and bn minus a and b plus absolute value of a and b minus ab. And now we can take a n out common from the first term and b out in common from the second term. So this is equal to absolute value of a n times bn minus b plus absolute value of b times a n minus a. Okay, and we want to make this whole thing less than epsilon, right? So how do we do that? So one strategy would be, okay, let's try to make this less than epsilon by 2 and let's try to make this less than epsilon by 2. Okay, so if b is 0, we don't really have to worry, this part is anyway 0. If b is non-zero, then what do we need to do? We need to make b times a n minus a less than epsilon by 2. I can divide both sides by absolute value of b and write it like this. So if I make a n within epsilon by 2 times absolute value of b of a, then I would have made this term less than this, the second summand here less than epsilon by 2. The first summand proves a little tricky, because now if I try this here, then I will have to make bn minus b less than epsilon by 2 absolute value of a n. But I want this to be true for all n large, and this thing, it's not it depends on n, it's something that depends on n, and this is going to cause a problem. So what we need to do is somehow bound this by something independent of n. Okay, and for that we will need a certain property of convergent sequences, namely the property that every convergent sequence is bounded. So I will call that a lemma. Every convergent sequence is bounded. Bounded just means that it has an upper bound as well as a lower bound. And let me just prove it. The proof is very simple. Basically, it's converging to some limit, so it's close to that limit, and so almost all terms are within, say, a distance of 1 from that limit, and then there are finitely many other terms to worry about. Okay, so let's write down the proof formally. Suppose a n is convergent, so that means that we have a limit, right? Limit n tends to infinity, a n exists. Let's call that a, the limit, let's call it a. Now I can take any epsilon. Now let's just take, so when you don't know what to take, you just take some normal, like some your favorite number. In this case right now my favorite number is 1. So take epsilon equal to 1, and this property that the limit of n tends to infinity n equals a says that there exists capital N, a natural number, such that for all n greater than n, an lies between a minus 1 and a plus 1, right. We say that an minus a is less than 1 in absolute value. So, so now what we have is that all the terms after the capital nth term lie between, they have an upper bound namely a plus 1 and a lower bound a minus 1. So, to find a bound for the whole sequence, all I have to do is I will take L, my lower bound, to be the minimum of, so I have to worry about the first capital N terms of the sequence A1, A2, A capital N, and then I will take A minus 1 and U equal to, so let L be this and U be the maximum of the first N terms A plus 1. Then what we have is for all n in n, L is less than or equal to an is less than or equal to U, because this is certainly true of the first capital N terms, because we here for L we have taken something that is less than or equal to all those numbers, and it is also the on the other side the first capital N terms are less than or equal to U, because we have taken the maximum of A1 An and something that could be even bigger. So, and then for the remaining terms, well, it comes from this property that if n is greater than little n is greater than capital N, then an anyway lies between a plus 1 and a minus 1. And so, what we have is an is bounded. Okay. So, that completes the proof. We write QED sometimes. And what I want to say at this point is that there is another way of writing bounded, and we will often just switch between these two things. So, suppose I take k to be the maximum of the absolute value of u and the absolute value of L. So, these things, you know, they could be positive or negative and so on. So, I will just take the, so this is something that is you know, it's greater than or equal to 0, but usually positive unless all terms in the sequence are 0. So, so then what we have is absolute value of an is less than k, well, I should say less than or equal to k for all n in n. So, this is another way of thinking about bounded sequences. A bounded sequence is a sequence which has an upper bound and a lower bound, or equivalently it is a sequence whose absolute value has an upper bound. Okay, so with this little bit of preparation, let us go back to our proof that the sequence A and Bn converges to AB. So, let us see, where was the problem? The problem here was that we have capital, we have this first term here which has this absolute value of An coming outside, and we want to upper bound this thing. So, we could certainly, you know, if since the sequence An is convergent, we could say that this is less than or equal to, so this term here is less than or equal to k times Bn minus B, where k is a bound for An. For all n in n. So, now we know what to do. So, I will choose, so here instead of this I can just put instead of absolute value of A n I can put k. So, now I am ready to write the proof, and it will be modeled on the proof that we had for the sum. So, we will choose n1 to make the first term small, we will choose n2 to make the second term small. We will make each term less than epsilon by 2, so that the whole thing will be less than epsilon. So, now choose capital N1 such that for all n greater than capital N1, we have Bn minus B is less than epsilon divided by 2k, where k is a bound for the sequence an. So, where k is such that absolute value of an is less than k for all natural numbers n. And this k exists by this lemma that convergent sequences are bounded. So, that will take care of the first term, and then for the second term we will choose n2 such that for all n greater than n2, an minus a is less than epsilon by 2b if b is non-zero, and if b is 0, do not worry about n2, just take n2 to be 1. Then in any case for all n, absolute value of an minus a times absolute value of b will just be 0, and so it is not really going to bother us in any. So, now take n to be maximum of n1 and n2. And if little n is greater than the maximum of n1 and n2, then it is greater than or equal to n1 and greater than or equal to n2. So, both these properties will hold that bn minus b is less than epsilon by 2k and an minus a is less than epsilon by 2 times absolute value of b. So, what we have is an bn minus ab. Well, as we worked out, this is an bn minus an b plus an b minus ab, which by the triangle inequality is less than or equal to absolute value of an times bn minus b plus absolute value of b times an minus a. Now, what do we know about bn minus b? Well, bn minus b is less than epsilon by 2k, and an itself is less than or equal to k. So, what we have is this is less than or equal to k times epsilon over 2k, and this is, well, absolute value of b times epsilon over 2 times absolute value of b, which is equal to epsilon. And so, the sequence a n bn converges to ab. The proofs of the third and fourth parts of this result are, well, the third part, the proof is very similar to that of the first two parts. The fourth part is even simpler. I'll leave these as exercises for you, or we'll discuss them in the tutorial.